Welcome everybody to this BAA webinar. I remember that we did something very similar to this back at the beginning of this year. I think it was the first week of January when we had Jim and Ashley give us a talk on the techniques that they would use in order to recover a meteorite if one happened. So all of the cameras and then the analysis and then the searching for it. And by some amazing piece of luck or whatever, we actually had within 2 months this thing that you can see on the screen here, the Winchcombe meteorite fell, picked up by a lot of cameras in the UK, some really impressive analysis done to determine where it fell, and then it was recovered very quickly. So it's great to have Jim and Ashley back to talk about this and give us the latest news on the Winchcombe meteorite. I've seen it in the Natural History Museum, and it's a great opportunity to go to London and see it. And I believe the driveway's there now as well, Ashley, is it? Or is that's on display too? So they even dug up a bit at the driveway that the meteorite fell on and put that in the museum too. So really looking forward to this, finding out about what's happened since the last webinar. And given how much predictive power there was in the last one, I'm expecting some really good predictions that turn out into real events in the next few months. So any more meteorites coming, you can do your magic on those. Anyway, so Ashley's going to start. We will go for about 45-50 minutes, and then, as is normal with the webinars, we'll take questions at the end. You can type your questions into the chat box on Zoom or the chat on YouTube if you're watching on YouTube. I'll pick up those questions and feed them to the panelists. So, okay, Ashley, over to you.
Brilliant, thank you, Nick. Yeah, just to add to, we do have the driveway. The driveway is not currently on display yet. It's quite big, it weighs a lot. We're working out what we're going to do with it, and we also want to try and do some science with it as well before we put it on display. But yeah, you can come and see, yeah, as you said, you've been to see the piece that's on display in the museum, and you can also go and see some bits of the meteorite on display in the little museum that they have in Winchcombe itself as well. So if anyone's in the Cotswolds at some point, I encourage you to pop in, and they've got lots of nice little display now of what we've been working on over the last few months. And so thank you very much for having us back. For those who don't know me, my name's Ashley. I'm a research fellow now at the Natural History Museum. So I've been working at the museum for the best part of the last 10 years, studying meteorites and studying in particular carbonaceous chondrite meteorites. So this has been an especially fun year for me. And as Nick said, that we actually, me and Jim gave a talk about how we were going to try and find the next UK meteorite all the way back in January. And I promise you, we didn't plan this, but just at the end of February, we ended up with the first meteorite fall recovered in the UK for 30 years. It's been quite a crazy 6, 7, 8 months since that happened. A lot of stuff, a lot of work has gone on. And so we're going to try in the next sort of 40 minutes, 45 minutes, give you a very brief overview of how we found that meteorite and some of the analytical work that we've been doing and what we're trying to learn about our solar system from the Winchcombe meteorite. And so you're stuck with me and Jim again this evening, but this really is a huge team of people. I think there's well over 100, and there's probably a few missing off of here as well, 100 people that helped actually find this meteorite, covering a whole range of different things. So there's the people who've got cameras. So I know many of you watching probably have your own meteor camera that actually saw the fireball when it happened. There are people who went and traipsed around. I mean, the Cotswolds is lovely, but honestly, in the beginning of March, it's pretty cold and damp. And so there's the people who actually went searching for meteorites. And then there's a whole load of us who've also been busy in the laboratories actually studying the meteorite for the last few months. And so, yeah, it's just me and Jim tonight, but there's a massive group of kind of scientists and citizen scientists that have been involved in this project. And I think we're going to kick off with Jim talking to you about the actual fireball event itself.
Yeah, perfect. Thanks, Ashley. Well, might as well start with a video of the event. And we're going to structure the talk with me talking just for a few minutes about the events of the 28th of February, then Ashley picking up really from the 1st of March onwards and the hunt for the meteorite, the analysis of the meteorite, and then me talking about videos again and camera systems. So This is just a tease. This is the only video in the first part of the talk, and all of the rest of them are in the end, just to make sure you stick around. So here you see Richard Fleet's video from Wilcott in Wiltshire, just about 7 seconds long. And you can see right now it's just coming into the atmosphere, then an enormous amount of fragmentation and brilliance, then tiny little pieces trailing off. So it's worth just running through again, sort of initial brightness, huge fragmentation, and then a whole lot of tiny fragments in a train, like a Starlink train at the end of the image. So it was something pretty special that we saw there. So actually, if we go on to the next one, please. Now, I'm not going to read this to you, but the first 90 minutes really showed that something big had happened. So the fireball was at 21:54, and Twitter and Instagram immediately lit up. And Will Gator, the astrophotographer and journalist, pointed out about an hour later that meteor was the 6th most popular search term, I think, on Google in the UK at that time. So 60 people pretty much immediately reported it through the UK MON or American Meteor Society site, and eventually 1,100 people reported it. It showed up on about 40 different doorbell cameras and showed up on about 16 meteor cameras. So if you want to go through that timeline in detail, it'll be on the YouTube version, but we can move on to the next one, Ashley. This is a map of where it was seen by the different meteor and fireball cameras in the UK. So it's seen from Manchester down to Honiton, and it was seen from Ireland across to Belgium, incredibly widely seen. Now you'll see there's a whole lot of different symbols on there. Each of the symbols corresponds to a different meteor network. There are 6 meteor networks, 5 different sets of technology, all observing the same event. And I've listed there the owner-operators of cameras who've caught this, sort of amateur observers. I haven't listed the credits for the Fripon network or the UK Fireball network, because it would have filled the whole page and then there'd be no image. But moving on from that one, Ashley, just plowing through. This is a set of images from the 5 different systems that caught the Winchcombe meteor. And what we had to do, I mean, each of these different networks, 6 networks, 5 technologies, all typically just do their own thing day to day, different sort of ethos, different objectives. But when a big fireball event happens, actually compare notes combine data. So we're able to pick up the data from all 5 systems. And for those of you who've used the Global Meteor Network system, you'll know the ECSV file is the way that data is transferred. Swap those around. Got a really good idea of what had happened. So that's what people saw early on. Actually, if you go to the next one. Looking at back to the map again and looking at the distribution, the 2 sort of institutional systems, UK Fireball Network and Scamp Fripon, got it from very different sides of the country. So the Fripon network got it from underneath the Fireball path. Fireball came in from the west towards the east, whereas Desert Fireball network got it head on. Now, by early the morning after the fireball, both networks had calculated trajectories and orbits. They were very, very similar. They weren't quite the same. So we were able to, fortunately, combine the data, pick up the data by about 20 to 6 or so, send it down to Desert Fireball Network in Australia, and they crunched the numbers again. And then moving on to the next one, Ashley, you'll see a very useful combined trajectory was pulled together by Desert Fireball Network. This picks up Nick's data. So our host was a contributor at that point, as Nick caught it on his camera in Chelmsford. It picks up the Desert Fireball Network data that came from the east of England, and the Fripon data, which came from Wales and the east of England, and got a very, very nice trajectory by combining them. So that's the power of the UK Fireball Alliance. We can actually swap the data around. It's really is a loose collaboration between the different networks and between the planetary science community, so that when you get a big fireball, you can actually go hunting meteorite. We were able then, early on the morning after, to come up with that red area that's marked there around Winchcombe. The blue area was also the strewn field, as it turned out. It's much smaller, but we went out to the public with a big area saying, if you've seen anything unusual, send us a photo. We're looking for a meteorite in this area. Now, we got lots of photos of bits of tarmac, of bits of brick, amazingly, all sorts of things. But we also, very importantly, got one spectacular photo that came through to UKMON on the evening of the day after the fireball event. So actually, I think I've got one more after that. Okay, so I just want to do a recap now. You can see here a good summary of what we knew in the hours after the event. And this came from Frippon, so the same thing would have come from Desert Fireball Network. And now UKMON can do something very, very similar the morning after an event. It can pull all the data from UKMON cameras, do the analysis, combine them, thanks to the work of Mark McIntyre. Reading these graphs from right to left, you can see that the meteoroid came in at about 13 kilometers per second, and then the speed couldn't calculate very reliably early on, dropped off quite quickly, and got down to about 8 kilometers per second before the Frippon system stopped seeing it. That's in the right-hand graph. In the left-hand graph, you can see that as the meteoroid came in, again reading from right to left, brightness steadily increased until it saturated the whole system, and then steadily decreased until it reached the limit of the Frippon system. So it's probably still luminous and still decelerating, but it's not visible. And you could even see the orbit calculated in the evening before. So that told us exactly where we were looking within that red zone. COVID meant we couldn't easily get together a search team, couldn't all rush down there. So had to rely on the media. And thanks again to Will Gator and to University of Glasgow media team, Natural History Museum for getting the press release out there. And it said that there was a very high level of fragmentation in the meteoroid, and that it came from an orbit going out near Jupiter. So we knew we were looking for something very fragile and a bit unusual. And the race was on to try and find it before it got rained on. So Ashley, over to you.
Brilliant. Thank you, Jim. Yeah, so Jim alluded to this picture already, but so the fireball itself happened just before 10 o'clock on Sunday, the 28th of February this year. And, you know, we went to bed, I think, or I don't know if some of us maybe didn't go to bed, but we were cautiously optimistic that maybe there were going to be meteorites on the ground in the UK. Obviously, as Jim mentioned, it was lockdown at the time, so we couldn't just jump in our cars and travel over there. And so we had this appeal in the media. You know, if you're in this kind of area around Winchcombe and you find some unusual rocks that have appeared suddenly in your front garden or something, give us a shout. And we were really lucky that the Wilcock family sent this picture to us via UKMON. And so we got this, I think, on the Monday evening. So it's been a long day of talking to radio and TV and things about the fireball. And this came through. And to be honest, I think many of us weren't, I mean, we thought it definitely could be a meteorite, but none of us were completely 100% sure at that time. But it was definitely went on our list of things there definitely wasn't a brick. So it went on our list of things that we were going to check out once we were in the area to actually search properly. And so what happened is I shared this with a few people in the planetary science community in the UK, and Richard Greenwood, one of them who works at the Open University, he was much more convinced than I was that it definitely was a meteorite. And so he managed to track down the Wilcock family on the Wednesday it was, and actually he doesn't live so far away from Winchcombe, so actually travelled over to meet them and confirmed very quickly that this actually was a meteorite fall that happened. And He gave me a call and sent me some pictures, and I was immediately, or as quickly as I possibly could, on my way over to the Cotswolds. What was really lucky for us was that Rob and Catherine Wilcock and Hannah, they didn't know it was definitely a meteorite at the time, but they had a suspicion that it could be. And so they took these photos. To give you an idea, this is about 20, 30 centimeters or so across. They're not geologists by training, so they didn't put a scale bar on, which is what we would normally do. But they realized it could be a meteorite, and they actually put some gloves on and they collected this material up about 12 hours after the fall. So it's pretty much as quick as you can get this. Really amazing. And they put it into these sealed plastic bags and they got in touch with us. So this was an absolute dream, really, for us. And me and Richard had an amazing night meeting the Wilcock families and their next door neighbor as well, where some of the sample had ended up. So as Jim said, the Fireball networks were also working out kind of streamfield for this, and we managed to organise a small search team to go over to the area, particularly once we'd confirmed that we had meteorites on the ground. This was incredibly challenging. It was the middle of lockdown. There were several different institutions, all with different paperwork, all with different risk assessments that needed to be done. I had a special letter from the Natural History Museum that, I can hear an echo. I had a letter from the Natural History Museum that gave me permission just to be out of the house, really, for work purposes. So we managed to do this, and the Cotswolds is not the easiest place to go searching for meteorites. You can see it's quite hilly, a lot of forests, a lot of rivers, a lot of rural land where you get lots of things that look like they could be meteorites. But fortunately, the team were in the area for about a week or so. Unfortunately, they were really successful. And so I'm sure many of you have probably seen a picture of this stone before. This was found by the University of Glasgow team on the Saturday after the fall. So that was the 6th of March. And it's actually the largest intact piece of Winchcombe that we have. So it weighs, it's a beautiful fusion crusted, slightly angular stone that was slightly buried below the surface of a field just outside. So it's about the size of a piece of cake. So this was an amazing find, really, and really showed how amazing, we can track these things and we can actually go and find them even in the UK. And so, in total, we have probably about just over 500 grams or so of the Winchcombe meteorite that's kindly been donated to the museum by the families. And so, so this is a picture. This is the Bond, This is the Wilcock family up here. This is Victoria Bond, whose land this stone was found on. We also, these are the Carrick family. They found some in their garden in the town or village of Woodmancote, which is to the west of Winchcombe. And there were a few other people who've found material in the area as well. And so we've been incredibly grateful that nearly everything that's been found has actually ended up in the museum for us to work on. And so in total, as I said, we've got just over 500 grams that was collected within 7 days of the fall. So we have that first batch of material from the Wilcox driveway. That's about 300 grams. That was collected within 12 hours. And then, within that first week, we have just over 500 grams. And it didn't rain during any of that period. So that's really lucky, particularly when we're thinking about carbonaceous chondrites. We want to look at their volatile compositions. There was some dew on the ground, but no significant rainfall. And apart from that large stone that was found by the Glasgow team, nearly all of it are really dark, kind of millimeter, centimeter sized fragments and powder. And so it's nice to have lots of material. And this is really handy for sending samples out for people, but it's a real headache for a curation point of view. And you can see this is just one batch of the small stones that we've been looking after. Many of these have actually have gone into oxygen-free environments they probably did them on the Friday after the fall, and they haven't been out of those environments since. We have a huge amount of material that we haven't even looked at yet. It was an incredibly busy time. It has been a busy year. So we did lots of press, lots of talking about the meteorite fall. Particular highlight for me has been getting into private eye and not getting into private eye because of scandals. So this was excellent to see this cartoon coming out. This is a picture of the half of that large stone that was found in the field. So actually, because it was embedded in the ground and these things are really fragile, when they pulled it out, it split into two separate pieces. So one's about 100 grams, and that's what's on display in the public galleries at the Natural History Museum. And then the other 50-gram piece is one of those stones that was put into a sealed oxygen-free environment, and we haven't had that out yet. And so you can see it's really dark in color. This is the fusion crust on the surface here. So you can see it's kind of got this kind of snakeskin type texture. This is the mud and things along the surface. And we have these white flecks, and that's probably carbonate minerals within this sample. So the Winchcombe meteorite, first meteorite fall to be recovered in the UK for 30 years. So it doesn't happen every day. It's the first UK meteorite to have a known pre-atmospheric orbit, and Jim showed you what that was, and I'll talk a little bit more about that in just a second. It's also the first ever carbonaceous chondrite meteorite that's been recovered in the UK. So we have about 25 meteorites from the UK, and nearly all of those are ordinary chondrites, and there's a few ions and things. This is the first carbonaceous chondrite that we've got. So when I say carbonaceous chondrite, what do I mean? Well, these are basically the oldest and chemically the most primitive meteorites that we have in our collections. They're incredibly rare. They probably make up about 5%. So we have something like 70,000 meteorites in our collections worldwide. Carbonaceous chondrites make up about 5% of that. They contain basically the building blocks for the solar system. They contain materials that formed just over 4.6 billion years ago, before we had planets and moons. So that really take us back to time zero. Many of those carbonaceous chondrites also contain things like water, and they contain really important organic type materials, things like amino acids that potentially played a really important role in bringing water and kickstarting life here on the Earth. So these are really the things that when we think about how the solar system formed and why we have life on Earth and potentially in other places in the solar system, it's the carbonaceous chondrites that give us a way to go back to look at what was happening at time zero. And so two of the biggest kind of questions we have about the carbonaceous chondrites is where do they come from in our solar system? So we have 70,000 meteorites, but for most of those, we actually don't really know exactly whereabouts they came from in our solar system. So we're really interested in trying to know what the source regions of carbonaceous chondrites are. And then we really want to know what that pristine volatile composition is. So what was the composition of a carbonaceous chondrite before it becomes altered or modified in the terrestrial environment? And Winchcombe is a really important sample that can help us understand that. One of the other ways you can do that is through asteroid sample return. And so it's trying to answer those two questions is part of the reason that JAXA and NASA have been investing kind of millions or billions of dollars in actually building spacecraft to go out to carbonaceous asteroids, collect material from a known location and bring it back so it's never seen the terrestrial environment. So JAXA have a mission, or had a mission called Hayabusa 2, which went to this asteroid called Ryugu, and this collected material and brought it back. Just completely fortuitously, but this came back in December last year, so not so long before the Winchcombe meteorite fall. And actually, to be honest, studying this material I thought was going to be what kept me busy this year. And I've been slightly derailed by working on Winchcombe, but I was just saying to Jim and Nick before I started this evening that I've actually been in meetings in Japan for the last 2 days. So I've been up all night and sleeping during the day. Because we're just getting to the point, we've been working on these Ryugu samples, and hopefully the first results will be coming out very soon. And then the other mission, the NASA mission, was OSIRIS-REx, which went to asteroid Bennu. And so those samples, it's a very similar type of asteroid, a carbonaceous asteroid, and those samples will be coming back in 2023. And we're really excited to look at those. And this is just a very quick comparison. So this is a picture of some of the samples that came back from asteroid Ryugu. So in total, they've got about 5.5 grams of material, which is much more than they were hoping to get. So we've been really lucky there. And this is a picture. This is one of the pots of Winchcombe. So this is about 40 grams or so of that powder that was on the driveway of the Winchcombe meteorite. And so you can see they look very, very similar to each other. Okay, so talking about the orbit for Winchcombe. So out of that 70,000 meteorites, we have pre-atmospheric orbits for about 30 or 40 or so. So really, really rare event. We're getting more now because we have these fireball camera networks. So the numbers are going up quite quickly. But really, it's a very small number of our meteorites that we have any idea about where in the solar system they came from. Winchcombe is the 5th carbonaceous chondrite fall to have a known pre-atmospheric orbit. As Jim said, we've got 16 really brilliant videos of that event. plus all the dash cam videos and doorbell cameras that recorded it. So it's by far and away the most widely documented carbonaceous chondrite fall that we have to date. And that means we have a really well-constrained orbit. And that orbit's shown on here. So Winchcombe here is shown in red. Just for comparison, I've got, this is the Maribor CM chondrite that landed in Denmark. And this is Sutter's Mill, which landed in the US, another CM chondrite. And so hopefully what you can see is that the orbit for Winchcombe is really similar to the orbits for Sutter's Mill, Maribor. And it's actually, there are two others. There's a meteorite called Tagish Lake, which fell in Canada, and there's a meteorite called Flensburg that fell in Germany in 2019. We have orbits for those as well, and they're slightly different. They're slightly different types of meteorite. They're ungrouped carbonaceous chondrites, and their orbits also slightly differ from what we see for Sutter's Mill, Maribor, and Winchcombe. So that's telling us that those CM chondrites are probably coming from a common source region in our solar system. And we know the semi-major axis for all three of those is around 2.5 AU. And so that actually corresponds to the 3-1 motion resonance with Jupiter in the main asteroid belt. And so it looks like that region is where we're delivering CM chondrites from to the Earth. And so that's probably telling us that the actual type of asteroid this came from was a C-type asteroid that exists within the main asteroid belt. So it gives us a really firm handle. We can't say the specific asteroid, but we can say really well that whereabouts in our asteroid belt these CM chondrites are probably coming from. And we also know these things came in really quick. So all three of them have what we call a cosmic ray exposure age. So basically the time between when it was knocked off the asteroid and made its way to Earth, that exposure age is about less than 1 million years for all three of those meteorites. One of the other ways we link meteorites and asteroids is by comparing the light that reflects off them. So when we look at asteroids, we look at the light that bounces back from the surface, from the sun, and we can do the same sort of thing in the lab, looking at the meteorite. And so this is just I wouldn't worry, it's a noisy looking line, but this is the reflectance spectrum from the Winchcombe meteorite that was measured very quickly after getting the sample into the museum. And you can see the overall reflectance is so this is value here. The overall reflectance is very low. That's because it's very, very dark. And we do see some features in here. So there's some kind of bumps in this wiggly line. And so this is this feature here just before 3 microns is water and OH. So I'll talk a little bit about where that actually sits within the meteorite. And then we have another feature here, which is CO3, which is related to the carbonate minerals. But really, I just wanted to make the point that this is very similar to the spectra that we see for C-type asteroids in the main asteroid belt. The entry conditions for Winchcombe were also slightly different from the other two. Excuse me. So Sutter's Mill, the meteoroid that hit the top of the atmosphere, was probably several meters in size. It was big, and it was also going really fast, up at about 30 kilometers per second, and it fragmented high up in the atmosphere before producing meteorites. Maribor was very similar. This is pretty much the only footage we have of Maribor, but it was probably, again, larger than a meter or so in size and going really, really quick. Winchcombe was very different. So as Jim said earlier, it hit the top of the atmosphere at about 14 kilometers per second, so much slower. And the body itself was also much smaller than the other two. And so we can tell this from the fireball footage, and we can also, we measure cosmogenic radionuclides, which we've been doing. And so the estimate really is that the mass of the object was about sort of 60 to 70 kilos, and the size of the object was probably much smaller than a meter. So it's actually the smallest instrumentally observed carbonaceous chondrite fall that we've had so far. So onto the sample. So one of the first things that we do is to measure bulk oxygen isotopic compositions, because they kind of act like a fingerprint for the different types of different types of meteorite groups that we have. And so I won't bore you with what all the different meteorites are, but these are all different groups. And so this was done at the Open University. Richard Greenwood, actually, this is his kind of specialist subject. And so we had these measurements done less than a week after the fall. So we knew very quickly what type of meteorite we had. And so Winchcombe sits right bang in the middle of there. Actually, we've done several measurements and it scatters around a little bit, but it's a CM chondrite. And we have about 500 or so CM chondrites in our collections. Nearly all of those were found in the cold desert environment in Antarctica, and there's a few from hot deserts. And there are some other falls. So Murchion's the really famous CM chondrite fall. And Winchcombe's a very similar type of meteorite. One of the other things that we do is we take little chips of the meteorite and we put them into kind of epoxy resin and we polish them flat, and then we study them using electron microscopes. And so this is an example of, we've done this, we've made about 20 or so of these polished blocks and distributed them to different teams in the UK, and also out, a few have gone off to the US and into Europe and to Japan and things. And so what we're looking at here, this is what we call a backscattered electron image. Essentially, the contrast is telling us a little bit about the chemistry in the sample, and you can also start seeing some features. You can start looking at grain sizes and understanding what the texture of this meteorite is. And Winchcombe, this is just an example of one of the blocks, but they're all quite diverse, but Winchcombe is very similar to, or very typical of a CM chondrite. And so what we can also do is collect element maps. And so this shows the distribution of iron, calcium, and magnesium. So iron in green, calcium in blue, magnesium in red. And again, we can start looking at the chemistry and the mineralogy of what this meteorite is. So Winchcombe, like other CM chondrites, it contains chondrules and calcium and aluminium inclusions, and these are the oldest solid materials from our solar system. So these are the first things that formed in our solar system. They're just over 4.56 billion years old. But in meteorites like Winchcombe, these have been completely replaced by phyllosilicate or clay-like minerals. So this tells us that the Winchcombe comes from a body that formed beyond the snow line. So there was ice there, and that ice melted and reacted with the original materials and actually completely transformed and made what we call kind of a secondary mineral assemblage. So all the chondrules and all the CAIs have nearly had all of their original mineralogy changed in the Winchcombe meteorite. And then those chondrules and CAIs are actually, you'll see, are set within this, what we call the matrix. It's really fine grained. Typically, it's submicron grain size. It's very, very iron rich. You can see some of it stands out. And that matrix is made up of a mixture of these phyllosilicate and clay-like minerals. We have some unusual minerals that we don't see so commonly on Earth, made by water, called dichilonite, things like magnetite. And you'll see the blue things on here as well. These are carbonate minerals. This is mainly calcite that we're seeing. So these are all things that formed through water-rock interactions that were taking place probably within the first few million years of the solar system. The other thing about Winchcombe, and this is also typical of many CM chondrites, is that it's what we call a breccia. So it actually has a mixture of different lithologies. So within those lithologies, we see variations in the abundances of the different minerals and the sizes and the compositions of the minerals change slightly between them. And so hopefully you can see in this map that in this top corner, my mouse, this top corner looks, it's just much coarser grain size. There's much more of the red stuff. This is olivine that hasn't been altered. So it's a very different looking lithology to this, which is very dichilonite rich. And so this is, again, as I said, is very common of CMs. And this is probably, we think the original CM body actually was probably quite large, and then it got smashed into lots and lots of pieces, and they kind of reaccumulated together to make what we call rubble pile asteroids. And so things like Rugu and Bennu are these smaller rubble piles that probably were derived from a bigger object originally in the early solar system. So that's probably when this mixing of these different lithologies was taking place. We also know for Winchcombe that it does contain solar wind. So it has a component in helium and neon that's been implanted from being exposed to the solar wind. And so that tells us that it's probably spent at least a period of its life on the surface of its parent asteroid. Okay, so I'm going to sort of play the video, but I'm not going to play all of it because it's quite long. One of the things we do with all meteorites or all extraterrestrial materials is try and do non-destructive work. These things are incredibly rare, they're incredibly precious. We want to minimize any destructive analysis we do, or at least do it after we've had a look inside. And so one of the best techniques for doing that is computed tomography, so CT scanning, which is basically just firing an X-ray through your sample, rotating the sample as you do that, and looking at how the things are being absorbed. And so certain phases will absorb the X-rays, the dense phases like metal or iron sulfides, magnetite, and they show up bright in the images. And then more porous things or less dense things actually show up slightly darker. So this is just an example. It's going through very slowly of a CT, one of the chips that we've looked at. It's completely non-destructive. So this is about a millimeter-sized chip. We've done this for lots of different chips, and it shows us really nicely that brecciated texture that we see. And we can also pick out some features in 3D that we can't do in 2D. So if I just go back quickly, so this is a big lump of probably olivine, I suspect here. So this is probably a chondrule. that we can see. And if we scroll through, so this bright stuff in here is not so clear. This is the chelanite rich phases. It almost looks kind of squished, like it's got some sort of petrofabric to it. And we do see that in other CMs. These brighter things are probably iron sulfide grains. They could be metal, could be magnetite. I think if I scroll through, so again, you can see bigger things coming up. I think if we go, hopefully, there we go. And this thing, this nice round thing comes in here. This is a really beautiful chondrule that suddenly appears in the middle of this chip. So we wouldn't be able to see that without doing the CT. We can see the exterior surface, but this is an amazing way for us to actually see what's inside that chip. And then we can decide how we're going to cut it to do the other types of experiments. So really handy technique, important for all extraterrestrial materials. Ooh. And the one thing we can do is actually take all those, so you basically create a stack of images and you can reconstruct those into these three-dimensional things. So the meteorite is not blue and green, we've just done that to make things easier. And so this is the stack created. And so you can see that chondrule, that really round chondrule just shows up there, and the big one just comes in here. You can see the kind of larger grain sizes, these bright things, these coarse sulfides seem to appear in this corner, but we see much less sulfide, much smaller, being able to quantify the kind of degree of brecciation and understand the alteration in the meteorite. So the other important thing are volatiles. And we always think of, so the Winchcombe meteorite contains about 12% water, and that's very typical for CM chondrites. And it's not liquid water, it's OH that's locked up within those phyllosilicate minerals, so it's bound within a mineral structure. And yeah, we always think of the Earth as being this incredibly wet place, but this is a really nice figure from the USGS that actually shows that the amount of, these blue dots are supposed to represent the actual amount of water relative to the size of the Earth. And so, yes, there's lots of water on the Earth, but actually compared to the total mass of the Earth, it's a really small component. And so it's always important to remember that, because you can do some kind of back of the envelope calculations. And it turns out that, if you make the last, or if you add 0.5% of the material accreted to the Earth, if that was a material that was very similar to the Winchcombe meteorite, that would also deliver all of the Earth's water. So really, you just need one asteroid that's very similar to the Winchcombe meteorite to bring all the water to the Earth. And so this is why we're so interested in studying these things and trying to understand their composition, is trying to understand, where did the Earth's water come from? And not only water, but also the real building blocks for life. And so it does also contain carbon. It's about 2-8%. So that's, again, very typical for CM chondrites. The isotopic composition is slightly different to many other CM falls, but not massively so. And that carbon is split up into lots of different components. So lots of it's in carbonate minerals. So this is just a nice picture, electron microscope image. And that is carbonate minerals formed through precipitation out of fluids. And so we can actually, what we're doing at the minute is dating the carbonates in this. And my guess is, if it's like other CM chondrites, these are probably formed within the first sort of 4 or 5 million years of the solar system. We also have pre-solar materials in the Winchcombe meteorite. So this is dust that condensed and formed out around stars before our solar system even formed. So this dust, these pre-solar things, are older than 4.56 billion years. And they're made up of things like silicon carbide, pre-solar nanodiamonds, we have graphite, we also have pre-solar silicates. In meteorites like Winchcombe, they're not so common because the aqueous alteration has actually destroyed many of them, but they are there in Winchcombe. And then the other thing we have are amino acids. And so very happy to report that we have definitely found amino acids within those Winchcombe materials that were collected really, really quickly. The abundance is quite low, but not so low as to be unusual. And that's probably related to the degree and the temperature of the alteration that was happening. But we do have kind of pristine amino acids within the Winchcombe meteorite. So I'm going to wrap up and then hand back over to Jim. Really just to re-emphasize the point that the Winchcombe is another data point for us in trying to understand the sources of carbonaceous chondrites. And it is by far and away the most widely documented CM chondrite fall. And so we have a really well-constrained orbit, and we're starting to see, 3 points isn't a lot, but we're starting to see a pattern that these things are coming from the main asteroid belt, which is really important for giving us geological context for our meteorite collection. It's also the most pristine member of the CM chondrite group. So Short of sending a spacecraft to an asteroid and collecting the material, you couldn't have got hold of this any quicker. So it wasn't that first material was collected within 12 hours, and sealed up into bags. And yeah, it's as fresh as we're going to get it. And it means we have an unmodified view of the kind of volatile history, or the history of volatiles in our solar system. And then it's just completely fortuitous that it fell whilst we have these two missions going on, but it's a really complementary material that allows us to kind of test analytical procedures when we start working on the Ryugu and the OSIRIS-REx samples. And so, Jim, I think back over to you.
Okay, well, thanks, Ashley. Thanks for that. And I did promise you videos, so I'll give you some. I've realized I forgot to say who I am and why I'm here. So I'm organizer of the UK Fireball Alliance. And so that's the consortium of networks who are cooperating to try and find meteorites once there's a fireball. Now, my aim from this point, my hidden agenda, is to try and convince you to get a fireball camera system if you don't already have one, or a meteor system. So it's coming up to Christmas, so either Santa Claus or your nominated person can go shopping for you. So think of this as internet shopping that's about to happen. This first fireball you're seeing here, which actually seems to have stopped, is not Winchcombe, but it's one that happened 2 weeks ago over Hampshire, as seen from Eastbourne, and it's pretty typical of things caught by the All Sky 7 system. I'm showing this one because it was a bit nearer to the fireball than the Ben Stanley's camera in Nuneaton was to Winchcombe. Gives you an idea of the sort of capture that you can get. Ashley, could you pop on to the next one, please? Now, this is Winchcombe, and this is seen by Dave Jones's camera in Chardon, Somerset. This is using a different system of the 5 that are available. It's UFO capture, and it's actually quite an old system now, and it uses a charge coupled device. So you can actually see that the image, it's very hard to work out exactly where the meteoroid is. And the technical reason for that, called blooming, is leaking of charge from pixels into the pixels around. So this is one of the reasons that I don't encourage people to go and get this system, though I think it's still pretty popular. There are a lot operating. And in fact, this one, just after Winchcombe, was dismantled, and Dave has replaced it with a global meteor system in the same housing, pointing in the same direction, waiting for the next Winchcombe. Ashley, could you on to the next? Now, this is Winchcombe again, and this is seen with the Global Meteor Network camera. This is Paul Dickinson's camera in Wiltshire. And the animation here is just taking frames from just the last couple of seconds. It was wildly oversaturated during the fragmentation. But you can see there's just absolutely beautiful detail here of the individual fragments of the meteoroid heading for the Wilcox driveway, or for Victoria Bond's field, or for Dan's solar farm. And you can see each of them pretty much. This is a very sensitive camera, and it caught an extra second of the trajectory compared with the Fripon cameras or Desert Fireball network cameras. And so rather than seeing the trajectory finish at 30 Ks up, it was down to about 27 or 25 Ks up. And that allows much more accurate calculation of the strewn field. So if you want to go hunting for meteorites, then having a big network of these sensitive cameras is a really good way of doing it. Actually, if you can move on, please, to the next one. Here is really 3 of the 5 possible meteor cameras, all on one chimney, and I won't say whose it is. But working from the left, there's the All Sky 7 camera, which has got 7 cameras in it, and it gave that purple image, the first one you saw. So just beautiful images, incredibly media friendly. The next one over is the SCAMP or Fripon camera, and that's the network that Ashley and I run in the UK. It's a French network. They cost about £2,000 each, and they're very suitable for institutional work. They're great scientific instruments, the image quality is, well, you have to be a parent to love it, really. They're not very media friendly. The third one over, halfway down the chimney, is the Global Meteor Network, which is run out of Canada. There are about 450 worldwide and more than 80 in the UK. And they cost less than £200 to build. And all of the instructions are on the internet. You order the bits off AliExpress and they arrive from China in dribs and drabs over a period of a few weeks. And then even I managed to put one together. I put 3 together. So they're pointed in different directions around. The 2 that I haven't shown here are the UFO capture, which is an old system. Richard Fleet got his lovely video on that from Wilcott. Dave got the video from Chard, but they're more difficult to extract data from. They cost multiples of the Global Meteor Network cameras, and they use the CMOS sensor, CCD sensor, which just makes life a little more difficult. So I've not shown a picture there. And then Desert Firewall Network, run by Luke and Sarah and others in Luke Daly, Sarah McMullen in the UK. Spectacular images, originally designed for the Australian outback. They take about 27-second images. And so anywhere that's got light pollution, you'll pick up a lot of bright sky. So really, Luke and Sarah and others run a campaign of putting them in dark sky locations around the UK, and 3 of them got Winchcombe. But moving on, Ashley, to the next one. If Santa wants to spend up to £200 on you, you can build your own RMS camera. This is how, these are the 2 main bits. On the left is a Raspberry Pi computer, and that'll cost you about £35 or about 55 if you buy the flash one. You don't need it. And on the right-hand side, a very cheap IP camera. It's about 32mm square, has a 4mm lens on it, and then all the rest is just making that work, power supplies and housings and so forth. All of the software is on a micro SD card. And so really, you will get change from £200 if you want to build this yourself. Actually, if we could move on to the next one. Here's Global Meteor Network camera coverage in the UK. And there are a couple of gaps left in England, but practically all of England is covered to a good degree now by Global Meteor Network cameras. And really, UK Meteor Network through Richard Kasserek, Pete Campbell-Burns, Mark McIntyre, Dave Jones, and I'm going to not give the whole roll call, but have had a very big push to just try and get these deployed. Now, if you want to get one, then the best place to point it is in one of the white circles. Scotland has got very little coverage. It has Desert Fireball Network coverage, but we had a week ago a big fireball that was caught from Gretna, but nowhere else. So no one really knows what happened to that one. And that's just 2 weeks ago because there isn't the coverage in Scotland. In England, there are 1 or 2 little spots which will get coverage from 15 different cameras, 15 different cameras of this network. But that's not a problem. So the more data you've got, the better constrained it is. And everyone gets their own image of the fireball event. So moving on, Ashley, to next one. Okay, this is my last slide. If you do want to get your own system, the best resources are on the UKMON website. 3 videos shown here that Dave Jones has recorded, showing how to assemble it, how to install it, really step-by-step guide. There's also a lot of additional information on the internet. And with UKMON, you get a digest every day of all of the meteors that were caught the night before. And also you get meteors live. So you can actually go to a page on the website and look at the meteors that were caught the night before and see them from all the different cameras across the UK. So I thoroughly recommend that. And so Santa's going to be busy. If you get active now, you could have your system running by Christmas, hopefully. That's my sales pitch. Thanks, Ashley.
Brilliant. Thanks, Jim. I think we can do some questions if you want, Nick.
Yeah, that's fine. Thank you very much, both of you. And I think this is a really good example of how people can get involved in science. So setting up these camera systems and then seeing what you guys do in analysis of the meteorites afterwards. It's just fascinating to see what comes out of this. So yeah, in terms of questions, if anyone's got any questions, you can ask them on Zoom or you can put them into the chat on YouTube. So I'll just go through the questions now. So Darrell Dobbs asked a question. He says, how much do you think you recovered compared to how much made it to the ground? So you said about 70 kilos at the top of the atmosphere. How much do you think got to the ground, and then how much of that did you actually recover?
So the prediction is, 70 kilos hit the top of the atmosphere, probably around half a kilo, that kind of ballpark made it to the ground. We know of about 600, just over 600 grams has been recovered. So I think doesn't seem like we're missing big pieces.
Okay.
So there might be a little bit, sort of tens of grams of small bits out there. They won't be in a good state anymore, I don't think. But I don't think we're missing a kilo or 2 kilo rock. So yeah, I think we did a very efficient job of collecting it, luckily.
Yeah, that's really good. Diane asked a question. She says, how much of the surface material has to be removed until you get to the pristine material?
So it's all pristine. When it comes through the atmosphere, it gets the fusion crust around it. And I guess if I go all the way back, apologies. The fusion crust is essentially the rock being cooked up as it comes in through the atmosphere, but it's only was it 7 seconds? Was that right, Jim? Is that how long the fireball was for? Yeah. So it's very brief, and rock does not conduct heat very efficiently at all. And so you can see here the fusion crust is only the outer layer. It's no more than about 1 millimeter or so thick. So that's kind of all been, and that's really interesting. It actually tells us some, and we have a group of people who've actually just been looking at the fusion crust, and there's some interesting stuff going on in there. But other than that, everything inside is pretty much pristine. Obviously, things, if they're just sat out in a field, the atmosphere, these are really like sponges, and so the atmosphere will get its way in there. And so this is why we put it in kind of oxygen-free environments really quickly. And that tends to do that from the surface outwards. So we tend to, we'll look for interior bits if we can, but most CM chondrites are not found within 12 hours. So this is all pristine.
So I guess, and that all comes down to the camera coverage we had then, so that we were able to recover it that quickly.
It's exactly that. We were. I mean, there was a lot of luck involved, but yeah, if we didn't have the cameras, we wouldn't have seen the fireball. If we hadn't have seen the fireball, we wouldn't have gone on the press or done the news. If we didn't do the news, the Wilcock family put that in the bin.
Yeah, so we definitely need to get those cameras in Scotland and Ireland and the places which haven't got such.
Absolutely, and so we want to cover the whole country because there are big areas that we're missing, and I think the model is maybe 1 meteorite fall a year or something roughly in the UK. So it's just not a very good place for finding meteorites. And as Jim said, we can't have too many cameras. The more cameras we have, the more videos we have, the better we can constrain those orbits. And the other really lucky thing we had for Winchcombe is that it was just really clear at that night. If it had been cloudy, we might have had 1 or 2 videos. So the more cameras, the better the chance we have of actually seeing that fireball. So.
Yeah. When we did the last webinar on this subject, there was a few things in the Q&A afterwards about what would happen if we did get a meteorite fall, specifically with regards to people walking off with the samples and how many of the samples would end up in private hands, how many would disappear, what would end up in the museums for scientific analysis. How did that work out in the end?
So there is a small amount of material that's in private hands, but the vast majority of it, the finders or the landowners really kindly donated it to us. So we went, we chatted to them, we told them why we were excited. I mean, that first night I spent, I don't know how many hours with the Wilcocks outside their house during lockdown. And I think we've just been incredibly lucky. They all got it. I think they all understood how important this was scientifically. It's a little bit of history in the UK. As I said, it's the first one for 30 years. And so we were really lucky that they all they all went, yeah, it's yours.
Yeah,
So,
no,
yeah.
that's really good. So it does seem to have worked out really well.
It's worked out. It's been amazing. Yeah.
Probably
It's been fantastic to work with the Wilcox, and I know they've had all the kind of glory. I guess they've had all the press, but I had the picture of the Carricks and the Bonds, and there's some other families that found things who just didn't want any attention, and they've all been, the whole community in Winchcombe has been a dream to work with. Really, we've had a lot of fun doing it.
So definitely a shout out for this Winchcombe Museum then, if anyone has
to go and visit. It's a lovely little museum. It's a beautiful part of the world. It's a lovely town. So actually when the meteorite came down, I was there for about maybe even less than a day, because I brought the sample back straight to the museum. So it wasn't until, when did we go? Went over in August, I think it was. We went to the Winchcombe Country Show to show off some bits and pieces. That was really fun. And then in September, we did a whole week where we visited all the schools in and around the Winchcombe area and around Cheltenham and Woodmancote. And it's just amazing. They've just been lovely and just helped us every step of the way. Yeah.
No, it's brilliant. And it's a really good example of kind of citizen science and everything else.
Yeah.
So a few more questions. Derek Poulton says, I live near Murchison in Australia, where the famous meteorite fell in 1969. How will Winchcombe be stored? He says Murchison is mostly stored in Chicago.
Yeah, lots of Murchisons at the Field Museum. I used to work at the Field Museum, actually. We used to have drawers and drawers and drawers of Murchison. so now we at the Natural History Museum, we've got drawers and drawers, well, a drawer or a box maybe of Winchcombe. So yeah, it's really interesting. So because we know the kind of history of this sample really well, we know what was found when. So as I said, that first material was really quick. We have the big stone that was found on the Saturday. Other bits were found on other days. We know what the weather conditions were like. And so initially it all came into the museum. The curators picked out a whole load of stones that have gone into as I said, these oxygen-free environments and have been sealed off. We will put there is some stones that have gone into nitrogen. Some will probably go into argon. So we'll actually be able to monitor how these rocks are modifying in a kind of really systematic way over the years. We'll keep going. We'll put them in different environments. We'll go back and study them and go, okay, that's how, if we do this, this is how it changes. And so that's really important, because it gives us a way to understand what happens to all the other CM chondrites that we find. And so, yeah, the other thing is we're getting a special, we're going to have it hasn't quite arrived yet, but we have purchased a kind of specialist glove box. So everything will be inside that glove box, so and sealed away as well. So, people can visit the collection and come and see it without us having to, at the minute, it's kind of in a box that we have to open and shut. So it's changes in things like temperature and humidity that are the worst thing that could happen to a carbonaceous chondrite. So putting it in a box and taking it out and putting it in a box and taking it out is awful. They will, and to be honest, we have seen really, really quick evidence of terrestrial weathering in some of the stones. Really quick, within a few days, I think. So
yeah. Okay, Steve Bosley says, Ashley, your element map was largely green, which was iron according to the key. So why was the meteorite so friable, or was the map not representative?
Oh no, it is iron, but it's not iron metal. It's phyllosilicate minerals. So the bulk iron content is it's about 20 to 30 weight%. So they're very, very iron rich, but that iron is in phyllosilicate clay minerals, and they are really soft. So imagine getting a piece of mud and drying it out a little bit. It's that kind, so it crumbles in your hand. So this stone in particular is part of the reason I don't putting it on display actually was incredibly stressful for all of us, because we hadn't touched it since it came in the museum, and then it's very friable. It's very, very fragile, this stone. So.
Okay. A question from Giles, and it's what do you mean exactly by a pre-atmospheric orbit?
So that's just the orbit before it entered the Earth's atmosphere.
Okay.
So those orbits are showing you what path it was on before it came in through basically the Earth got in the way. So everything gets knocked off an asteroid and it starts making its way in towards the sun, and we just happen to get in the way.
Okay. Okay.
Yeah, if I could add to that, the Desert Fireball Network team in Australia did something quite cool, which was using the very precise orbit calculated by Dennis Vida in University of Western Ontario. They then rewound it 50,000 years, in fact further than that, to actually look at its interaction with the rest of the solar system over that time and try and work out roughly where it went. Anything more than about 50,000 years and your measurement errors get far too big. But I don't know what the science yield of that was, but it was sort of quite cool to see that they've done that.
Yeah, yeah. I mean, and I guess the more accurately that we can characterize the orbit from multiple camera views, then the more accurately these integrations can be done before you start hitting all the chaotic effects of perturbations and things in the solar system. So.
Absolutely.
Stephen King says, what would be, if he came across a meteorite or something that looked like one, what would be the best way to pick it up and keep it pristine?
Really the best thing to do is to put some gloves on and pick it up and either wrap it up into some kind of cleaned aluminium or clean aluminium foil, or put it into a clean plastic bag and just seal it away. So they're obviously not completely airtight, but it's better than it just being out in the atmosphere. So, and then don't put a magnet on it. Is the other thing not to do. So,
yeah. So
we've learned some stuff about magnetics, and we have done some magnetic measurements in Winchcombe, and it tells us a bit about, particularly the morphology and textures of the magnetite minerals, which is related to the kind of compositions of the fluids on the parent body. If you put a magnet on it, we lose that record. So,
okay, right. And I noticed that there seem to be quite a lot of Waitrose containers for the.
Yeah. Just by weirdly, I think that so yeah, I mean that was just a strange. They put things into Waitrose bags and Waitrose yogurt pots, or I think they were cream cheese pots or something like that. We have all of those in the collection now, and I hope at some point we'll be able to put things like that on display. And there's a whole lots of fun WhatsApp messages between me and the rest of the meteorites community that happened at the time as well. So hopefully at some point we'll have a bigger display than we have now. But yeah, just by chance, the head of PR or something at Waitrose was visiting the museum that week that we got the meteorite in. It was very weird. Right. So it's bottom of my list of things to worry about, but it's just a strange coincidence.
But if you find any organics in the meteorite, then it's mainly Waitrose cream cheese.
Waitrose cream cheese, yeah. Yeah.
So a comment here from Ian Williams saying, if anyone's traveling to Prague, there's an impressive meteorite collection at the National Museum there as well. So I know, around the world there are, but Natural History Museum certainly got one of the best, I think, from sort of going around different museums around the world. Lots of comments from people who are looking to set up various camera systems. I can certainly say from my personal experience that building the GMM cameras is really pretty straightforward. And as you say, Jim, you order the stuff from AliExpress in China and it kind of comes anywhere between a few weeks and a few months later, and then putting it together is really straightforward. And the software and everything that drives it is really good, and you don't really need to worry about that. As you say, it's all on an SD card. So it sort of generally works out the box, which is really, really good. A few more questions. One from Derek Paulton says, does the meteorite have an odor?
Yeah, I actually personally haven't really smelt a particularly strong odor from it, and I do grind it up a lot of the time. A lot of the work I do involves turning it into taking the chip and grinding it into a powder. And I haven't actually noticed a particularly strong smell. But when the group at the Open University, when they did their measurements, they did describe it. I think it's gone into the official classification. They did say it smelled a lot like compost. And these things do tend to, I know certainly so maybe, yeah, when we open up some of these bags. So I know, for example, we've got a really nice piece of Murchison at the museum that's in a sealed bag. And every now and again, occasionally we'll open it up, and you can. So it may have been in there, or it has been in there for years, and you do get a really strong smell. So maybe in a few years, when we start opening up some of those other stones, because this is the important thing for us, is that we've had a sample that we've been working with for the last few months or so. But part of the reason we have collections is to curate these things and look after them, so that people will be working on this meteorite for for the next 100 years, 200 years, we have lots of questions that we want to try and answer using it now, but the questions that we have about our solar system will change with time. The analytical techniques we have will change, and so I'm sure it will smell very similar to Murchison.
Actually, Nick, could I pick up one of your earlier questions actually about ending up with dealers or ending up with the museum? Just want to say that a lot of the dealers have been very helpful in cooperating with the museum to actually describe what they've found. And also wanted to mention Dan Kirk and his team at Toucan, who went hunting for meteorites and found meteorites on their solar farm and then donated them to the museum. So just wanted to reiterate the collaborative nature. People sharing their data and sharing their finds and sharing their information has been fantastic. And I just hope that we can continue doing that, because everyone gets to find out what this thing was if we do that.
Yeah. I mean, it was logistically, this was really difficult because of the lockdown. We couldn't just get, ideally, if you're looking for a little black rock in the UK, you kind of want as many people as you can deal, as is practical to go traipsing around those fields, and we just couldn't do it. It was, I can't tell you. I was quite lucky that the stress that went into just allowing me to leave my house and travel across there for work was it was there was the excitement of the meteorite, and there was all the paperwork that had to be done, and it just wasn't practical to get everybody out there searching in the fields. So, but as Jim said, everybody's been incredibly helpful, incredibly useful, has been sharing data. We really, this is a real success for the planetary science community, and hopefully it's been it's gone really well, and hopefully the next one will go just as well.
So Michelle Kirk's been posting some links on the chat to some pictures of recovering bits of the meteorite. I mean, it must have been a really exciting time to be picking those things up from the ground. So really good. I think that's pretty much it. Questions. So I just wanted to say that thank you very much to both of you, Ashley King and Jim Rowe, for a really interesting description of essentially following up on what was the webinar that you did in January, which was looking forward to the first UK meteorite recovery, to actually having one and then doing all this analysis. It's just fascinating to see what you've done. I think it's really an important point too, that all of this comes from having all of this camera coverage across the country, and the more people we can get involved in that, the better. And also the work that Jim's been doing on making the different networks able to share data, I think is really important too. So that's great. So hopefully, we'll be back here again in a year's time or so, and there'll have been another of these.
Not too soon, I hope.
You'll need lots of glove boxes, Ashley.
Well, March, April, Ashley.
Pardon?
March, April, maybe.
Well, it's you're in charge.
So I'd just like to say as well that we've got Dr. Sarah Russell talking at the Christmas meeting. So our Christmas meeting on December the 4th, which is open to everybody, is going to be at the Royal Society of Medicine in Wimpole Street. It's not going to be at our normal venue, the Institute of Physics, because they've got a few problems with the building at the moment. So that'll be at Royal Society of Medicine, December the 4th, and Dr. Sarah Russell will be talking on the Winchcombe meteorite as well. So another opportunity to get some interesting information on this.
I'll try and make sure she doesn't have exactly the same set of slides.
Yeah, thanks, Ashley. So but it's just been absolutely fascinating, and for me to actually see this thing in the museum when my cameras had videoed it falling down through the atmosphere was quite a buzz as well. So thank you very much to both of you. I think we've done pretty much all the questions. I hope everybody enjoyed it. See everyone at the Christmas meeting on December the 4th. Thank you very much, everyone.
Thanks, Nick.
Brilliant. Thanks, Nick.
Cheers. Bye.
Bye.